Hello, I'm Sriram, and today we are going over AP Chem Lesson 3 Activation Energy. So this will be kind of a quick one because most of it kind of relies on stuff you learned from last unit, thermochemistry. In fact, we'll do a quick review. They're in a system. We can always say that our enthalpy is shown as change in H. If the change in H is the change in enthalpy, if the change in H is positive, the reaction is endothermic because heat is going inside the system. If change in H is minor, negative, exothermic. Heat energy is lost, meaning like the reaction is giving off heat. I usually just remember negative as giving off heat. So in order to react, molecules need something called as activation energy. Because for three reasons actually. One is to form products. Um, well, simply put, number one is original bonds must be broken. Number two is that this requires energy because you need energy to break bonds. Three, and simply enough, slow molecules. So if it's really slow, so no kinetic energy, very little molecules can't react when colliding. So with this being said, we have came up with this thing called activation energy, which is just a term saying activation energy. And this is also known as EA. And it's the minimum energy needed for a reaction. And EA is specific to one reaction itself. You can't use the value of, I don't know, the formation of water vapor to like the formation of carbon dioxide. And if you were in AP Bio or currently taking it, I think you kind of skimmed through this a bit during the last chapter, but you were learning about enzymes. It's kind of like the same thing. Ineffective collision, basically the opposite of an effective collision, as in last lesson. Of an ineffective elective collision is when two things collide, but they don't have enough energy or they're not in the right orientation. So they don't break current bonds and the reactants are still present. Nothing happens. Effective collision is what we want and what actually matters for the rate of a reaction. I think you get the idea from lesson 2. So what's the example of I think you guys remember these diagrams, right? The energy over reaction, or basically time, energy, and this is over the course of a reaction. So this is basically energy of the system. Well, we know that, let's say, I think here we have NO2 and then CO becoming NO plus CO2. So right now we have a reactants at the very start, just NO2 and CO. And there's some minimum energy here, but since it's not enough for them to become the product, which is NO and CO2. So actually, what happens here is what if we supply the system some amount of energy, and we call this EA. This is activation energy. And let's say we give it 132 kilojoules per mole. They're the units. So this is basically the activation energy. We give it, this is the minimum energy required for a reaction to take place. And then remember, this here is going to just be your change in H. So it's pretty handy, right? The top above is just EA, the activation energy. Below is just change in H. So because this is how much heat you gained or lost. And you actually lost some heat here because you started with a higher energy and ended with less energy. So this is actually negative 226 kilojoules per mole. But what's the main point here is that this is you give it 132 kilojoules per mole extra, and now you can do the reaction. And this is called the transition state, and we'll talk more about it real soon. In fact, right now. So transition state is basically like a little like intermediate because there's at one point of the reaction you just have the reactants. Another point of the reaction you have the products. So surely something over time during the transition state, there needs to be some small period of time where the reactants take time to form products. And it's either when like everything's broken up or something like that. But we actually have a term for it. So this is basically called the activated complex. And it's usually the peak of your energy diagrams. And it's actually unstable because obviously it has a bunch of energy. That's the peak of your energy. And it's going to be unstable because the more stable you want a system to be, the more bonds it usually has. So activated complex, just unstable atoms formed at the peak. And it's only momentarily because obviously then it's going to be formed into products. And activated complex, we also call it as the transition state. So overall, we basically have an endothermic and exothermic. The graph here is going to be pretty simple for both of them actually. Something like this. This is reactant. This is products. This is a transition state. Something like this. This would be EA, and this would be change in H. And change in H is positive for endothermic reactions. Exothermics. We start here, we go up a bit, and then we go all the way down. And so a change in H is going to be negative, and this is activation energy, and this is the peak, so transition state, reactants, products, and that's, yeah, pretty much it. Catalyst. So now we can, they're the sixth factor from last lesson, like where we talked about all those six factors, and the sixth one was a catalyst, and it says like odd one out, that stuff. Well, catalysts actually do something really useful, which is kind of why we are talking about activation energy in the first place. The reason is what catalysts do is able to do is it lowers the activation energy required. So the orange line is without catalyst, so the activation energy is gonna be this high. However, but with the catalyst, you can see the activation energy decreases a lot. So it actually speeds the reaction up because you actually only need a small amount of energy. So that's basically what a catalyst does. So let's look at a sample problem real quick. Actually, one more thing is that two extra ways to get more molecules to have enough energy, and other than catalyst, obviously. Well, the first one is just give them more heat, add energy, change the enthalpy. That's pretty much what we did in thermochemistry. The second one is add a catalyst. Okay, apparently adding catalyst was another one. But yeah, nothing new here. Never mind. Something new here though is new because it's kind of we already went through this both in Honors Chem and this year. It's the Maxwell-Boltzmann distribution. It's basically saying um, so the distribution of molecules, a lower temperature, they're kind of on the left, and this is kinetic energy or how fast the molecules are moving, and this is just distribution of it. So that's the most molecules will be moving this fast, kind of like that. Um, at a higher temperature, however, it kind of goes around here where most of the molecules are this fast, but usually it's only this fast, kind of that thing. Um, at any temperature, there's a wide distribution of kinetic energies because like there's so many small particles around. Some particles might collide more than others, and this ends in this various change in kinetic energy. The kinetic energy temperature is actually just defined as average kinetic energy. That's basically what temperature is. So, and obviously we know that higher temperature means faster reaction rates. So pretty much higher temperatures, more molecules have more energy. And let's say we have something that shows the activation energy. So something like this is EA. If the dotted line represents the activation energy, as the temperature increases, so does the fraction of molecules that can overcome the activation energy value. Just look here. Here we only have like, this is, I guess, for the orange line, I guess only like 10%. It's a bad diagram, but like we can say 10%. Here, how under for the red line, we can look at the graph, look how much space is under the red line bounded by the purple line. It's like twice as much, right? So activation energy, as it gets harder, more molecules can overcome the barrier. So that's basically how we can tie this in with the maximal Boltzmann distribution. So once again, quick practice problem. We have this little graph here, and we have a well-known um, equation here. So real quick, try to determine by yourself. Let me draw this graph again. Try to find by yourself, and if this is potential energy and this is basically the reaction pathway, is this endothermic or exothermic? If you said endothermic, you would be correct because the potential energy of the system increases, right? And if this is reactants, this would be products. And so why would the activated complex be? It would be right over here because this is the peak. So this is um, activated complex. So what would be the um, energy activation energy? Well, it's basically the difference between the peak and the initial starting point of the reactants. So this is going to be EA. Finally, what would be the change in, you only notice though, what would be the change in H? It would just be this over here because that's how much heat we gained after the reaction. So that's pretty much how to use these diagrams along with more new terminology like the activated complex. That's basically a summary of this lesson. Thank you.